In this bonus, we're talking about concept of prediction interval. Um, there are a couple of reasons I'm going to talk about this prediction interval and why I do not include this in the regular lectures. And first, let me talk about why I include this, because up to this point, we have always talked about estimating parameter values. We talked about inference, and when we mean inference, what we mean was basically we had again our population with unknown parameters. We would like to estimate them using some estimators, using some statistics. That was basically this approach, and this was called actually inference. And we obtained these statistics from those samples, and said the inference was from the sample to the population approach. On the other hand, one thing that is very much important, or two very important applications of statistics is statistical quality control or statistical process control, in which, okay, inference of these population values is a very important topic, but also monitoring the future values, future sample values is also important. What I mean is that we may have a couple of samples at first, or let's say that we have a single sample. From that sample, we are going to come up with some population parameter estimates, but then once we have those, we are going to control the so-called control charts. We are not going to usually have a single sample, by the way, but that's not the point. I'm not going to go into statistical process control in detail, but we are going to be using these parameter estimates for future, or for monitoring the future samples, just like this one. So we are at time 0 here, where we collect this first initial samples. By the way, this is called phase 1 in statistical process monitoring literature. And we obtain these values, these parameter estimates. But from now on, we are going to, in the future, when t is greater than 0 values and it hasn't come to pass yet, we are going to be obtaining sample by sample from the process, and we are going to be comparing the statistics from these samples with those parameter estimates. So it's not only inference, there is a second phase here. We are going to be interested in future sample values. And another very hot application I may say of statistics is statistical learning or machine learning. And most of these two topics are involved with the problem of prediction of the future value of some samples, of some given predictor values, which in the linear regression part I'm going to talk about. How can we find a prediction of the response variable? So here again, in the so-called training phase, we are going to have some samples. From those samples, we are going to be obtaining a model. That model is going to be similar to population parameter estimation procedure. But once we obtain this model, we are going to, so the first part will be again inference. But once we are through with the inference phase and we obtain the estimates of necessary parameter values, then we are going to use these parameter estimations for prediction. So here there is a subtle difference between those two words, estimation and prediction. Estimation, the word estimation is usually reserved for parameter values or model parameters. So usually we estimate parameters, estimate the population parameters or model parameters. Population model. Although I haven't talked about model, what a statistical model, I'm going to talk about in lecture 10, which is going to be about linear regression. So anyway, we estimate these population and model parameters. On the other hand, we usually predict future samples. So once we estimate these parameters, we use it. So this is called the inference step. Once we are through with the inference step, we use these parameter estimates to predict future sample values, response variable values. So that's One reason I would like to go into the concept of prediction, and another reason is I'm going to talk about this. This is going to be a more important topic in lecture 10 when we are talking about linear regression and least square analysis. And the reason I do not include this in regular lectures is I don't want to lose the momentum of the course, which is about inferential statistics or introduction to inferential statistics. Prediction is actually kind of next step here. And for the statistics, for the single parameter statistics that we are dealing with right now, prediction is a secondary issue. Nevertheless, I put this as a bonus video and talk about this one. So what do I mean by, I have already erased the heading, prediction intervals. All right, here is the problem. Up to this point, what we had was, we had a sample X, I call it. We had, or let me put it that way, we had a sample like this, X1, X2, Xn observations. From that sample, or using this sample, and assuming that X is normal distributed with unknown mu and unknown sigma square, for instance, we used X bar as the sample statistic, right? And S square as point estimators of mu and sigma square. And that was the inference approach. What we have never talked about is this. Once we have these observations and we come up with these predictions, point predictions, and also interval predictions for mu and sigma square, for instance, what we haven't covered is, what if we are going to obtain a future sample value, xn plus 1, or actually it may be more than 1, it may be n plus 2, n plus 3. So it goes like this. What about the future values? What do I mean by that? Can we find a confidence interval for xn plus 1? What do I mean by that? Let me rewind a little bit. We have obtained this sample from our process and observations, and we come up with these inferences, and we come up with these population parameter confidence intervals. What I would like right now is this hypothetical question. If I take another sample or another observation from that population, so this is one sample from that population, and this is going to be a single observation, which I haven't yet taken from this population. Yet what I would like to determine is what we call a prediction interval for this observation, so that I can guess what the future values, where the future values may lie. So this is a different question compared to this, for instance, a confidence interval for mu, because confidence interval for mu is essentially, if you recall, we obtain an interval like this, which is equal to 1 minus alpha, and lower and upper values are random variables, whereas mu is a population parameter. On the other hand, this is itself a random variable. So where one may ask, what is the practical application of this question? This type of question may have very valuable practical applications. For instance, okay, let it be something like this. Let's say that we produce samples at different concentrations, right? Actually, we have a target concentration, right? But due to inherent variability of our process, these different concentrations are obtained with a variance equal to sigma square value. So, and think of, let's make the question a bit more dramatic, and we would like to see whether it is possible in the future to obtain a high concentration or very low concentration product from this process. It may be such that a very high concentration value or a very low concentration value may be poisonous for the people who use that chemical. So we would like to see, and note that this is not, one may think that this is related with mu. It's not. Actually, mu is just the population parameter. It gives an idea about both the point estimate of the location of the data, right? So if it's our distribution, we are only interested in location of data, or a confidence interval related with this location of the data. We are not up to this point. We were interested in individual observations. If in the future, if these values were like from 10 to 2 to 10, let's say, is it possible that in the, or with a certain probability, of course, we can obtain a value of 12 or minus 1? Well, of course, in this case, it's not going to be concentration, but something else, whatever. So can we obtain those extreme values from that population just by looking from that sample? This is the question, and this is the concept of where the prediction comes into play. So it's about samples we haven't collected yet. So now if we get rid of these, now comes the statistical part. Always write a couple of forms. Actually, it's very simple to handle this whole issue. So what we are interested here is going to be, we have x1 to xn observations, and this is going to be our initial sample from which we are going to be obtaining x bar and s square, and we are talking about an hypothetical future or potential sample that may be taken in the future. So first of all, since actually we are going to be obtaining x bar here, let's see what is going to be, for instance, this difference, the expected value of xn plus 1 minus 1. One may say, why did I bother with this, or why did I use this expression here? Let me talk about it. Actually, the idea comes from control charts. And I think I tried to, at least try to explain this in a bonus video. In control charts, we have a center here, which denotes the target value or the mean value of the process. In this case, x bar is going to be an estimate of that. Actually, if you draw these values x1, x2, x3 to xn, they are going to be like this, scattered around the x bar value, right? If they were scattered around the x bar value, actually x bar wouldn't have been found as a sample mean, because these values will be equal to the sample mean. And also note that xi minus x bar, if you add these values from 1 to n, this is actually equal to 0. That's why I drawn these crosses, one up, one above. It's not possible that they are going to be all on the positive or negative side, because this x bar is taken as an average center of mass of these equal weighted observations here. The center of mass usually I refer to the probability density functions here. So here we are talking about single observations, so you may think about them as equal weighted observations. Anyway, so here the question, or so what we expect is, for any observation, or how we measure how we measure the relative location of each observation, is by finding that observation, its absolute position, for instance, is x3 here. But when you subtract from x bar, this gives us the relative location of our observation. So it's going to be in positive direction. So for a future observation, we would like to have an idea about this new statistic. Call it, for instance, deviation of n plus 1 observation here. All right, so the question that we are interested in is, first of all, what is the expected value of that statistic? Very easy to handle. Expected value of xn plus 1 minus expected value of x bar. Note that this is equal to population mean. Note that this is equal to population mean is going to be equal to 0. No big deal. That's great. So we have found what this statistic is going to be equal to. Now, expected value. Now, what is the next thing that we are usually interested in? Variance of the n plus 1. Once we find this expected value. So this let's say the first thing that we have determined in terms of its statistical properties. Now we find the variance. Variance of xn plus 1 minus x bar. Now, this is equal to the very important point. The next observation, xn plus 1 observation, which haven't occurred yet, are going to be independent from all these observations. And actually, again, note that each of these observations are independent from each other. And xn plus 1, which hasn't been, I mentioned that again, but since they are already independent, the next one is going to be also independent. But to understand it better, this one hasn't been sampled yet. So therefore, we can write this as a summation of two random variance of two random variables. So this is going to be simply equal to sigma square, which is population variance, because we are talking about a single sample, and this is going to be equal to sigma square over n. Therefore, what we have here is sigma square 1 plus 1 over n. So this is this dn plus 1 statistic, I may call. We have found its expected value and we have found its variance. Now the question is, what about its distribution? Very easy. Xn plus 1 is normal distributed. X bar is normal distributed. A linear combination of those two, this is going to be normal distributed. Now let's write the mean value. Mean value is going to be equal to 0, and the variance is going to be equal to 1 plus 1 over n. So we have a very nice statistic here. So now let's finish the whole thing. So, and if we know sigma square, that's fine, but usually we would not be knowing sigma square. So for standard error of the n plus 1, we are going to be using its estimated value. So it's going to be actually equal to a standard deviation estimate of, so this is going to be times 1 plus 1 over n. Actually, let's write, because I have reserved this for calling it, I have reserved this for the standard deviation estimator, which is the denominator of n. So let's use this one. It's going to be s1 over n. Therefore, now what we are going to have is our old t statistic. T0 is going to be equal to our dn plus 1 minus 0 over standard deviation of this the sample multiplied by square root of, oh, by the way, there is square root here. I forgot, I'm sorry. Oops, 1 over n. And instead of dn plus 1, we can write it that way, minus x bar divided by s1 over, and this is going to be t distributed with n minus 1 degrees of freedom. Why? Because S is computed from n samples, all right? But actually S has n minus 1 degrees of freedom because it's obtained from this sample here. From this sample here. So therefore, now we have a very nice relation. This n minus 1, so given some alpha value, we are going to be interested at t alpha over 2 minus n minus 1, whether the quantity that we find t0 is going to be between those two values or not. Actually, now it's very easy to find a confidence interval. We can write the same thing here. So it's going to be, let me actually write it here. It's going to be easy for me. Probability of this quantity and xn plus 1 minus x bar divided by s, and this is going to be equal to n alpha over 2 n minus 1 with 1 over 1 minus alpha probability. So if you take all element here to the left to this side and do the whole simplification here, what we end up with will be something like this: x bar minus the alpha over 2 n minus 1 times standard deviation 1 over n is going to be, yes, this is going to be xn plus 1 x bar plus t alpha over 2 s1 over n with a probability of 1 minus alpha. Now this is pretty much similar to the confidence intervals that we have found, at least in architecture or due to the terms, but there's going to be an important difference. Remember, if we had written a confidence interval, two-sided confidence interval for mu, it would be like this: t alpha over 2 n minus 1 standard deviation of square root of 1. And for square root of 1, I'm going to write it this way so that you can appreciate the similarity better. It's going to be x bar plus t alpha over 2 n minus 1 s1 over n. And even let me put a 0 here so that you are going to even see the relation, I hope. More clear now. The only thing that differs here is we have 0 here, we have 1 here, right? The very same thing here, 0 and 1. So one may ask, why do we have 1 here? We should go back to the derivation there. Now we are talking about single measurements. I repeat again, it's not the population mean. So since we are talking about single measurements, the population variance now cannot be divided by 1 over n. Actually, you are going to ask, where does 1 over n come from? I'll come to that in a minute. But this standard deviation will directly be effective on the standard deviation of this dn plus 1 term. Because actually what we are interested in, if this per mu, this was simply just deviation of any observation from the mean value. Therefore, its standard deviation is going to be population standard deviation. So actually this here 1 is just refers to that s here. So the population standard deviation is directly transmitted here in the final result. But it is even more, there is also a 1 over n element which actually increases than the standard deviation element. So this result is going to be noted greater than standard deviation. It's going to be in square root 1 plus 1 over n. And since 1 is actually, if we had only used 1, that would be equal to s here. But since we have 1 over n here, this is going to be greater than 1. So this whole thing is going to be greater than sample standard deviation. So why is this the case? The reason is now we have an additional uncertainty coming from the estimation of the mean value. If we had only mean, population mean here, then the variance of the n plus 1 would be equal to simply equal to sigma square. You can actually very easily see it from the derivation. That would be the only term. But we also have some uncertainty coming from the estimation of x bar value. So these two are added together. So this is our prediction interval for xn plus 1. Now, as a simple question, actually, from your textbook, I'm going to just abbreviate the question. I'm not going to go into the details. It's a question about tensile adhesion test on specimen. And so what we obtain is, as I said, I'm going to skip the story of the question. We employ 22 experiments and we obtain x values. And from those x values, x bar is found to be equal to 13.71. And standard deviation is found to be equal to, from that sample, is going to be equal to 3.55. The question is, find the 95% prediction interval. So what does it mean? If now this says 22 experiments are conducted, so the results of the experiments are x1, x2, all of these. Actually, so I'm not going to write each of the values, but the values may be like, I don't know, 12 something, 10 something, 20, not the problem, 20 is too much, 15 something, all these values here. An additional value here, if you take another sample, what is going to be the 95% confidence limit for that sample? So again, I emphasize this is a different problem compared to confidence interval. And this question, actually, in this question, first confidence interval has been shown just to demonstrate the relation between confidence interval and prediction interval. This is the confidence interval. Now note that prediction interval is going to be much greater than these values. Should be much greater than these values because it is the population mean. The population mean, the sample mean, as you can recall, is a pretty much small variance. On the other hand, this variance is now going to be added with the variance of each observation. So we are just going to use this equation here, right? We need this value here. So T alpha over 2 n minus 1. So T alpha over 2 is 0.025. N minus 1 is 21. So here I'm going to find these values from MATLAB. T inverse is the command, is going to be equal to 0.975 with 21 degrees of freedom. There is one unnecessary zero, I guess. All right. Now the way MATLAB uses is we write here with the T inverse command. Here we write the cumulative distribution function for the T distribution, while T 0.05 is the right tail side probability or area. We write the left side probability area, which is 975 with 21 degrees of freedom, which is n minus 1. So this value is equal to 2.0796. And what else do we need here? Let's see. We need the standard deviation of the sample. So it's going to be S is 3.55. And what else do we need? We need square root of 1 plus 1 over 22. So it's going to be 1 plus root 1 plus 1 over 22, which is going to be equal to 10225. Note that this is slightly larger than 1, and that's why it's that slightly larger part is related with the uncertainty of the sample mean. So this quantity here is going to be simply equal to, let's see, x bar 13.71 minus the t value 2.079 multiplied by standard deviation 3.55 and multiplied by this value 1.0225. Smaller equal xn plus 1, smaller equal 13.71 plus, let me find this value here, 2096 times 3.55 times 10225. All right, so this number is equal to 7.5. It's abbreviated, so it's rounded. So it's going to be 755. So the result is going to be equal to, if we call it, for instance, S is equal to answer. So 13.71 minus S and plus S is going to be equal to, so our prediction interval is going to be 6.2, smaller equal n plus 1, smaller equal to 31.3. So we are going to have a confidence prediction interval for xn plus 1 with a at a confidence level of 0.95%, or sorry, 95%. So the very whatever we have done previously in terms of confidence interval, the same logic applies. So 6.2 and 21.3 is the 95% prediction interval, whereas 12.14 to 15.28 is the confidence interval for mu. As you can see, this is largely smaller or significantly smaller, and the upper limit is significantly larger compared to confidence intervals. So that is actually one way of using these prediction intervals, and that may be helpful in many cases. Actually, I haven't exactly connected to this to the control charts or statistical process monitoring. Let me talk in 1 minute about that. Actually, as I shown you, and I cannot, here. Not only this is a center point, but we also have upper and lower confidence limits here, or upper or lower control limits here, usually in using the nomenclature or the terms used in a statistical process control. And usually these values will be found by x bar. So if this is x bar, this is going to be x bar plus some constant times standard deviation, whereas this one, this lower limit, is going to be x bar minus some constant times standard deviation. And those constants, for instance, can easily be, for instance, determined from this quantity here. Note that this prediction interval here consists of T alpha and this one. So if you call these two, product of these two as K, what we have here is, let me write it that way, x bar minus Ks, smaller equal to, of course, I should have mentioned here, this should be the product K. So I'm referring to this part, x bar minus Ks, xn plus 1 plus Ks is equal to 1 minus alpha. And K here is going to be equal to T distribution value. I'm not going to write the whole thing. 1 plus 1 over square root of n. So what I mean is, if not a single observation, but you have the potential to sample xn plus 1, xn plus 2, many observations. So what you do is actually you can easily construct a chart like this here. This is going to be x bar. This is going to be x bar plus k times s, where k is equal to t alpha over 2 n minus 1, and this is square root of 1 over n, right? And this lower limit is going to be xks, where k is, of course, the same value. And using these dashed lines, and even you do not need to show it, but let's also show it. We can show xn plus 1, xn plus 2, all those future observations. Where do they fall? We expect that with 95 or 99 or even with higher confidence level, we expect that they are going to fall within that interval. So one is here, another one is here, another one is here. Let's say that xn plus 4, this is here. Then since this observation is not within those prediction intervals, then we are going to deem, or we are going to think, or we are going to assume that something may be wrong with the process, because now we are outside of the prediction limits.